A step one question then from 2008, it's question number 9. It's also question 5 from the step 2 mechanics support module. First thing to do in mechanics always is to draw the picture. So we've got two particles, P and Q, each mass M on the diameter of a large hoop like this. P is the one on the floor, it says. That's fine. And the radius of the hoop is A. And now this hoop spins around. It doesn't slide. So P doesn't maintain contact. It doesn't slide over. It turns over. And P and Q both move. For example, if it turns over theta, you end up with this situation here, is what it's talking about. And now it says, write the coordinates of P relative to where it started in terms of theta. So, okay, well, if we look at this little triangle here, we have a little triangle there. Radius is, of course, A. And so this is A cos theta and this is A sine theta, which means the vertical distance P has traveled is not hard. That's just going to be, of course, all of this A. We just want this little distance here. So it's going to be all of this A minus A cos theta. So that will be the vertical distance. Now, its horizontal distance, you actually need to think about more carefully. It's not quite this. It seems very tempting to think it's this because it's just minus A sine theta. It's side here. It goes to the left, so it's minus A sine theta. Except it's not quite that because you've also got to think that the entire hoop has also moved. So what it actually is it's this distance minus this little distance here. That's the distance that P is going to go in total. So what is this distance? Well, if we look up here for a second, the distance that it goes around the edge of the hoop is just A theta, because it's just, R theta is just the arc length of a sector. So that means that this distance that it traveled along is just A theta. Imagine this turning over. We can put the A down here. It's just gone that far along to get to its new base. And then we just need to take away the distance that it's gone that way instead. So it's going to be, our thing is going to be this, A theta minus A sine theta, and then what we said for the y coordinate. And that's perfect. And now all we need to do is differentiate that to find the velocity, because of course the position differentiated with respect to time is the velocity. Now to differentiate this with respect to time, theta is a variable. A is a constant, so that's fine, but theta is a variable. So we need to differentiate that like we usually would, but then just slap on a d theta by dt afterwards. So theta differentiates to 1, slap on a d theta by dt. Sine theta differentiates to cos theta, put on d theta by dt. Cos theta differentiates to minus sine theta, put on d theta by dt. Except they're indicating that we should be writing those as theta dots, so that's what I'll do, which is there. And now to find the speed, I'm just going to find the magnitude of velocity. So I'm going to do this thing squared plus this thing squared square rooted. Expand some brackets here, you get a squared theta dot squared minus 2 lots of the cross term, which is actually going to be a squared theta dot squared cos squared. And then plus this thing squared, so a squared theta dot squared cos squared. Sorry, the cross term shouldn't be a cos squared. The cross term should be minus 2 lots of a squared theta dot squared cos theta. And then, of course, plus this one, and then this one squares to just this. Cos squared plus sine squared is 1, so you can factorize out the a squared theta dot squared, which you could have done right at the start if you wanted to. I just didn't. You end up getting this, because, of course, this plus this is just essentially makes one copy of a squared theta dot squared, which adds to make this, to make 2 copies of them. And then at this point, I just decided to leave it at that, I think. Yeah, I just did. Okay. And now it says, next thing, it says determine its speed, show that the total kinetic energy. Now, kinetic energy is a half mv squared. So all I need to do is do v squared as just this. But I need to find that for both p and for q, right? So I just decided to do the entire thing again with respect to q. So I found its position. So its position, well, it's moved across, well, it's gone upwards. We could say its position upwards is a plus a cos theta. That's its position upwards from 0. We're doing it with respect to where it started, rather than start with PM down here. So that's kind of our 0, 0 point is what we're saying. So its new vertical coordinates a plus a cos theta, and its horizontal component, of course, is going to be a sine theta plus that entire turn of a theta that we saw earlier. So it turns a theta, that's how far it's gone across, and then we add this a sine theta. And now I differentiate that to find v. I've done it much quicker this time. And then when I do that, I'm going to find the speed of that by squaring both components. Again, it's the same kind of expanding some brackets here. You get virtually the same thing. This thing squares to a positive, which is great. These things still combine, and the only difference that's made here is that because that's a positive, this cross term was also positive, and that's the only difference. And now, of course, the total kinetic energy is just a half of this thing squared plus half of that thing squared. And of course, the square roots are just going to go away when you do that. And when you expand out the half m's, you just notice that this term is going to cancel with this term. And you're just going to end up with 2 lots of this thing here, which is what they wanted you to get. And now finally it says, given the only external forces on the system are gravity and the reaction force. Well, there has to be a reaction force because otherwise the thing will sink into the table. There's a very useful show that the hoop rolls at constant speed. Now, if it rolls at constant speed, that means that the theta dot is constant. That's essentially what they're being asked to show, because that means that the rate of change of theta is the same, which means it rolls around at the same speed as it goes along. Because of course theta is going to be proportional to the arc length. It's just r theta. So of course so that means r theta dot is proportional to r to the amount of arc length you've traveled along, which is of course what the speed essentially is. So we're showing that theta dot is constant. There's a very useful thing in the book that I found. When no external forces other than gravity do work on a particle during its motion, the sum of the kinetic and potential energy remains constant. That was very useful for this question, and that just came out of the textbook. Now, the fact that there's a reaction force doesn't matter again. That just has to exist. It always does. And it's also perpendicular to where the thing is moving anyway, so it wouldn't be part of this equation anyway. But what I can just say is that the kinetic energy plus the gravitational potential energy is just constant based on this theory here, which is very useful. And well, the kinetic energy is just this. We described it earlier. The gravitational potential energy is just mgh, I guess, mgh, where h for P is the vertical position of P at any point, and for Q, the vertical position of Q at any point. So this is mgh for P and mgh for Q. Of course, the cos thetas cancel here, which is very nice. And now that's clearly a constant because m, g, and a are all constants. M and a are constants, which means for these two things to always add up to make the same number, a constant number, we require theta dot to be constant. And therefore, it's going at constant speed. And that's the whole question. Thank you for watching.